SWI stands for Study Group Wiskunde met the Industry, which is the Dutch version of the Study Group Mathematics with the Industry. And the idea of such a study group, so the study group itself is a one-week workshop. The basic idea is that the organizers invite 5 or 6 companies that pose a certain problem, which the company thinks that this could be solved or tackled with mathematics. But they themselves, they don't have the capabilities to tackle such a question. And the idea is that then a certain amount of mathematicians assemble during that week. And on Monday, the companies present these projects. And then people select one of the topics that they think they can work on for 1 week. Then they do work on that project for a week. And on Friday, they present the solution or an intermediate solution to the companies and to the other participants of this SWI.
My project with the company Synopsys was about the placement of microchip. So in mathematical terms, you have a lot of small rectangles and you want to put them in an efficient way in a big rectangle. So it's nice because it's a simple to explain. Everyone can imagine this. What maybe one cannot imagine is that it's very difficult to find suitable algorithm for this problem, and it's not a new problem, but then you can of course add some specificity, like some margin between the rectangles. You can optimize the place that you have in the middle or on the boundary, so there's all kind of things you can add. But the problem itself is well known, and still there is not an optimal way to solve it. So it's a vivid field of research. The new approach was to combine different approaches. So the Synopsys project has the advantage that at the end of the computations, you can verify what your algorithm gave you. And you can verify it on a computer. You don't need to build a chip to know how to place the microchip. So you can verify it, and then with different algorithms, you can compare the solution, take the better one, throw some away if they are not okay. So that way is very interesting to see all the different algorithms and to have a real possibility to test all of them and a real way to check what they do. Maybe it's nice to work on a project that is not my field of research, that I wouldn't have encountered otherwise. So I learned a lot during that week, and yes, I was happy to be part of it.
So this project was about creating a digital twin of a foot, and this was in collaboration with Fontys, University of Applied Sciences. They have a project called SmartScan, and in many applications or medical applications you have patients and they have some problems with their foot and walking around, so they may stumble and then they can get injured, and if you have other disabilities or other illnesses, then you can have, of course, a lot of problems afterwards. So in order to prevent this kind of stumbling over your foot, you often get a prosthesis, so something like a correction of your foot. And you build that into your shoe. You may have seen these inlays in your shoes. And someone has to make them, and someone has to basically get this shape of this inlay first. So what is usually done right now is they take some plaster, take it around the foot. They make a foot model with this plaster after drying, and every doctor who is doing that, or an orthopedic expert, has a different opinion, what is a good shape, and it's very, you have to be a master in that topic. It's not so easy to make that transferable and to discuss about, because a lot of is how you feel about it. It's a lot of experience. It's not A or B, it's, you have to feel it. And now this project is about to make this a bit more quantitative so that people can exchange about that. And how you can do that is, or this is the project about, to make a digital version of the food. And in principle, you can already imagine that nowadays we have a lot of imaging techniques. So like laser scans, they can make easily 3D models out of objects. But this does not really work here, because this orthopedic expert, they touch the foot and they feel it, and they squeeze it in certain positions, and they look how the patient behaves and how much pressure they can apply, etc. And then that means that the doctor or the orthopedic expert is in the line of sight of these imaging devices in general. So they replace these imaging devices now by a glove. And on the glove you mount position sensors, and later on, this was not yet in the project, later on they also want to add pressure sensors, so that you can basically track the motion of the glove around the foot and the leg, and also track how much pressure was applied. So the aim is to remove actually this individual feeling, which is not really objective but subjective, by objective data. And this data is measured by sensors that are mounted on a glove that is then worn by the orthopedic expert. And from that movement over the foot and leg, they make this objective model. Okay. And this is the aim of that project, to make this process from the data that has been collected already. So there is a huge data file for the sensors that are mounted on the glove. They collect X, Y, and Z data for position in space over time, and then per finger you have a sensor, so you get a lot of data stream. And our task was to translate this into a 3D computer model that you can use for visualization and further manipulation. A follow-up is planned, and I don't know exactly when this will happen, but in the coming weeks we want to discuss with people from Fontys University about a meeting and how the methods we developed so far can be put forward to make this product a success.
Yeah, what was my project about? It was about detecting diseases, like severe diseases such as cancer, at an early stage, which is still something that we're missing at the moment. And doing so by taking samples of people's urine and analyzing this. So that's what the company, You to Yourself, does. In your urine, there are small particles which are called microRNAs, and these can tell you a lot about what a health status of a person is. And so the question was in that project, how can we, based on this data, make inference on the health status of a person? And the complicated part was that there are so many different kinds of these particles, and so far it's a very new thing. Only very few samples were available. So for statistics, people who do know things about statistics, it's always important to have big samples. That makes things a lot easier, but we have very small samples, like 20 people, and thousands of these different kinds of particles, and that makes the analysis very hard. So there are a few of these, let's say 2,000 roughly particles, are known to be connected to certain kinds of diseases. So for certain cancer types, some of these particles are known to be related to that, but So this is still very new and not so much is known. So where comes mathematics into this project? So there are different things that relate to mathematics. So on the one hand, so it's data, and so data typically come with some randomness, because we never know like what a person did maybe before, the day before they gave their sample. So maybe it's they have an infection already, and then that's in that sample, or maybe they have some other issues, and that will also show. So in statistics, we always have to take these uncertainties into account, and that's a branch of mathematics. So typically we're not just suffering from one thing, but also have other things that might influence these concentrations. And to kind of separate these different reasons for why certain numbers are higher from each other. And that's also one part of mathematics, like deconvolution, maybe for those who know what that is. So there's a lot of math, and so uncertainty quantification, and also saying in the end. So in the end, this is supposed to be like a method that is applied really in healthcare, and there we need guarantees, right? So how certain are we about certain things that we're saying, but also we need to kind of say like how many times do we actually need a person to come in and give a sample, and how often do we need to do that? So quantify things, that's of course also mathematics. So there's lots of math in there, There will be a follow-up. So we're working right now on writing everything up. So there will be proceedings, and so we will of course write down our findings, but also, well, I know I will keep working on this problem because I find it fascinating. And I do believe also that others are going to work on it further,
So what was our project about? So I was part of the Glider project, and I was happy to be the coordinating person for this. This Glider project is in a way very different from other projects because this is driven or initiated by an artist, Zoro Feigl, who works with technical devices and does art with that. And so Zoro has a problem that is very nice to explain, I would say. This is about a glider, like a vlieger in Dutch, that should be kept in the air by some device, and that's in this case a robot. But first of all, the problem is, or the phenomenon is, that if you have some airflow, then this airflow can be used to keep this glider up in the air. And the goal is to keep this glider on a, say, pre-described trajectory where this glider should stay. And eventually the goal is to do so by using a robot arm. And this robot arm has a panel in its hand, in its arm, that creates this airflow. And this airflow is then constructed in a way that this glider stays on a pre-given trajectory, or at least in the air. So what kind of problems arise in this context? Well, the first thing is that it's quite difficult to find out what these dynamics are that create this airflow that leads to this glider to stay in the air. And well, the mathematical description of that is even more complicated than just the physical laws, because, well, you can imagine that this airflow is something that follows many, or is subject to a lot of perturbations. So wind, of course, is a problem. So we tried in the very first approach to keep this as simple as possible. But the underlying equations, so to say, are quite complicated, and we were soon facing the decision to make some simplifications here, quite severe simplifications. And then, of course, the question is, to what extent does this really mimic reality? So this is not really clear. And this is one of the biggest challenges here. And also the data of these, these experiments that Zora has made before. Well, they are there and it seems to work in a way, but to get this data connected to our models, this was really a challenge for us. So what is the follow-up of this? Well, this is an interesting point, because I think there's much more to come, so this was only the very start of it. Well, I think with what we have seen, we got a glimpse of how these dynamics work, and the next step is then, of course, to control or to proactively see what we can do in order to steer this glider to a pre-described destination.
This year's SWI, I hosted from the organizational side a project that was provided by PostNL, the largest Dutch mail delivery company. And the problem they provided us is the following. So you can think about their so-called distribution network, which means that you can imagine that mail is produced every day, everywhere in the Netherlands. And then there are some sorting centers, maybe close to a bigger city, where all that mail is collected at a certain time. And then towards the end of the day or maybe the early morning, this mail should be brought to different sorting centers, which could be maybe on the other side of the Netherlands or close by, and to be finally distributed to the recipients. But of course there is at one such place, there is incoming mail with all kinds of destinations, right? So there could be a certain amount of mail going from here to there, and you can imagine that PostNL has some estimates about how much mail typically is sent over here, and they might have different data for different seasons. Say over Christmas there are more packages produced or something like that. And it's not too effective for PostNL to actually send a truck carrying all that mail, say every hour or every 2 hours from each such sorting center to every other, because that's just too much effort and the trucks would be nearly empty. So it makes sense to aggregate the mail, which means that they have certain intermediate places where now the option is that trucks carry mail from close by sorting centers to such a intermediate station, and then some other truck can carry it further, and then it's redistributed at a later point. And this way, because all these routes are shorter, there is a lot of potential to actually save costs or save driving hours or whatever. And our goal was for the given data that the PostNL provided, figure out what is an optimal way of transporting all this mail through their network that they have available.
Well, I think the SWI is something that should or does attract students, but when I say students, well, we often mean PhD students actually, so of course this is different type of person, or also like a different type of background you have in comparison to, for example, a bachelor or master student. So I'm not sure whether this is that suitable for these early career students, because I mean, it is not much time in order to conduct this problem, and well, the more experience you have already with doing similar things, the quicker you can pick up the topic and do something. Because we shouldn't forget, I mean, nobody actually in this group ever had seen such a problem before, so this was really something new to everyone.